You're floating in deep space, 13 billion years ago. The universe is only a few 100 million years old. And somewhere nearby, a star the size of nothing you've ever imagined just detonated with the force of 100 normal supernovae. The shockwave is coming, the radiation is coming, and a handful of ancient stars are sitting right in its path. So how did any of them survive? That's exactly what this video is about. And here's the thing. Most people assume that if you're close to the universe's most powerful explosion, you're dead. But the real answer is so much stranger than that. Because some of those stars didn't just survive, they're still out there today, carrying chemical confessions from stars that died 13 billion years ago. And in one case, we've identified a single living star that is almost certainly the direct child of one specific ancient star we've never even seen. And by the end, you'll understand why the universe's deadliest explosions were, in some ways, surprisingly bad at killing things. Because most people don't know that 99% of a supernova's energy did absolutely nothing. When a massive star explodes, it releases an almost incomprehensible amount of energy. We're talking about more energy than our sun will produce in its entire lifetime, released in seconds. But here's the part that breaks your brain. Roughly 99% of that energy escapes as neutrinos. Neutrinos are particles so small, so weakly interacting with normal matter, that they pass through entire planets, like the planet isn't there. Right now, trillions of neutrinos from the sun are passing through your hand every second. You feel nothing. So when an ancient star exploded and a neighboring star sat right next to it, close enough that you'd think it would be vaporized, almost the entire energy budget of that explosion passed harmlessly through its core. The most deadly part of the blast was essentially invisible to it. The star didn't feel 99% of the most powerful explosion in its neighborhood. That is the foundation of how early stars survived at all. Because the 1% that wasn't neutrinos, the radiation, the shockwave, the raw electromagnetic fury, that still should have been enough to sterilize everything nearby. The ancient stars that were most at risk, the very first stars, called population 3 stars, were made of almost pure hydrogen and helium. No carbon, no iron, no oxygen. Astronomers call heavy elements metals, and population 3 stars had essentially none. That made them accidentally armored. Heavy atoms absorb radiation efficiently. They grab photons, they heat up, they get pushed around by radiation pressure. Hydrogen barely does any of that. So when a massive radiation front from a nearby explosion hit a population 3 star, the star's own chemical simplicity meant the radiation just passed through more easily. It couldn't grab onto anything. The most primitive stars in the universe were shielded by the very thing that made them primitive. Being made of nothing was a form of armor. But wait, because even with neutrinos doing nothing and hydrogen deflecting radiation, there were still gamma-ray bursts. And gamma-ray bursts are a completely different category of terrifying. When the most massive ancient stars died, some of them didn't just explode outward in all directions. They fired a focused jet of pure energy, moving at nearly the speed of light, in 2 opposite directions. The energy in that beam is so concentrated that it can sterilize a planet from halfway across a galaxy. If you were in the path of one, you were gone. But here's the thing about gamma-ray bursts that almost nobody talks about. That jet is only about 1 to 2 degrees wide. 1 to 2 degrees. The full circle is 360 degrees. So statistically, the overwhelming majority of neighboring stars were never in the beam at all. The universe's single most energetic events had catastrophically bad aim. Being a neighbor of a dying ancient star was far safer than it sounds, because the deadliest shot fired in a cone so narrow that most of the universe never saw it coming and never had to. But if you think the physics of survival is wild, the chemistry of what came after is even more insane. Because some ancient stars didn't just survive nearby explosions, they survived by exploding themselves weakly and then swallowing their own wreckage. Not all early supernovae were violent. A subset of ancient star deaths produced what scientists call a faint supernova, an explosion so underpowered that most of the heavy elements it created, the carbon, the iron, the magnesium, didn't escape. They fell back into the collapsing core. The star essentially ate its own explosion, and we can detect this today. Certain ultra-ancient stars alive right now have bizarre chemical ratios, specifically way too much carbon compared to iron. That ratio doesn't make sense unless the iron was swallowed back and the carbon escaped. It's a chemical fingerprint of a specific type of death that happened 13 billion years ago. We're reading autopsy reports of stars we've never seen. And in one specific case, we're reading the biography of a single individual star. The star is called Hei 1327-2326. It's alive right now. And its chemical composition is so precise, so unusual, particularly its extreme carbon enrichment, that models point to it having formed from the remains of one specific population 3 star, somewhere between 25 and 60 times the mass of our sun. Not a class of stars, not a general era, one star. We are reconstructing the life and death of a star that lived 13 billion years ago from the chemistry of its child, which is still burning today. That is one of the most extraordinary things in all of modern astronomy. Not all ancient massive stars exploded. Some of them just vanished. Stars between about 140 and 260 times the mass of our sun were completely destroyed by what's called a pair instability supernova. The explosion was so total, so complete, that nothing was left behind. No neutron star, no black hole, just gone. The entire star converted to energy and scattered. But stars above 260 solar masses, they skipped the explosion entirely. They became so massive that when they died, they collapsed straight into a black hole with barely a flash. The universe's biggest stars died the quietest deaths. No dramatic explosion, no chemical fingerprints scattered across the galaxy. They just silently disappeared. And that silence is actually a problem for astronomers, because we can find the children of stars that exploded, stars like He 1327-2326, carrying their parents' chemistry. But the children of the silent giants, we can't identify them the same way. There's no confession. There's no chemical autobiography. The most massive things that ever existed left the least evidence behind. Now here's the final piece, and this one is still unsolved. We don't fully understand why some ancient stars exploded and others didn't. Inside a supernova, the outgoing shockwave actually stalls. It hits the dense inner layers of the dying star and it stops. Whether it reignites and produces a full explosion or fails and collapses into a black hole is decided in a window of milliseconds. And the deciding vote? Neutrinos. Those same particles that pass through everything. A tiny fraction of them deposit energy back into the stalled shockwave. Just enough, sometimes, to restart it. This is called the neutrino reheating problem, and we have not fully solved it. The deaths of the universe's first stars are still, in part, a mystery. We don't know exactly why some of them exploded and some didn't. We don't know exactly how much energy got deposited back into each shockwave. We are still, in 2024, working out the rules of the universe's very first deaths. Some ancient stars may have survived simply by being alone. During the universe's first few 100 million years, stars didn't form evenly. Some formed in dense cosmic filaments, packed close together, surrounded by neighbors that could explode, but some formed in the great voids between those filaments, completely isolated, no neighbors, nothing to explode near them. If any of those void stars survived, and some theoretically could, they'd be drifting through intergalactic space right now, unchanged since the beginning of the universe. Some anomalous ultra-metal-poor stars found in the outer halos of galaxies might be exactly this. Relic population 3 stars, living fossils, from the universe's first chapter. We haven't confirmed one yet, but we're looking. So let's bring this all together. Ancient stars survived the universe's deadliest explosions for reasons that should not work. 99% of supernova energy passed straight through them as neutrinos. Their chemical simplicity accidentally deflected radiation. Gamma-ray bursts fired in beams so narrow that most neighbors were never in the line of fire. Faint supernovae swallowed their own wreckage and left chemical confessions in their children. And some ancient stars survived by being so cosmically alone that nothing could reach them at all. The universe's deadliest era was also somehow survivable, not because the explosions were weak, but because the universe is enormous, neutrinos are ghosts, and hydrogen doesn't care how loud you are. And somewhere out there, a star called He 1327-2326 is still burning, still carrying the ashes of a star that lived and died before Earth existed. A biography written in chemistry, a survivor of the universe's most violent beginning.